So this panel is the future of energy, Stanford's big, clean energy gamble. Well, we don't really know if it's a gamble or not, but we wanted to be a little bit provocative in this. Somehow, these gentlemen have talked Stanford into spending an awful lot of money on a very innovative approach. And so this panel is about giving them the opportunity to describe that to you. We have Jack Cleary on my far right. He is the Associate Vice President of Land, Buildings, and Real Estate. These are the folks that made and run this beautiful campus. In the middle, we have Ron Gawer. Ron is the Director of Energy Operations at the new Stanford Energy
Facility.
SESI. What is SESI?
SESI.
So it's more than that.
It's more than that. Yeah.
All right. Well, anyhow, he'll describe that for you, and he really understands how this all works. And then we have Bill Kelly. Bill is to my far left. He's the Vice President, Commercial Americas for SunPower. And you'll find out why Bill is on this panel shortly as well. So if it's okay with you gentlemen, I'd like to go ahead in that order, give you each an opportunity to do some introductory remarks, and then we'll open it up to questions. I'll try the first few, and then we'll open it up to the audience. Unfortunately, we only have an hour, but I think we'll be able to get it in. Please, go right ahead, Jack.
Okay, so I guess it's...
It looks amazingly like my presentation.
All right, good afternoon. I'm here with my compatriot, Ron, and he is pretty much my partner in crime for this big project that we have called SESI. And SESI is more than just an energy plant. It's a series of initiatives, as you'll see, which is securing Stanford's energy future well into the next few decades. So, you know, with the question that Jeff asked when we were asked to be on this panel was, you know, why did you do this? And I think there's an easy answer, which is we're nearing the end of the life of our cogeneration plant, which was built in the 1980s. And we had to think of what was going to be next. And we could continue to invest in the current technology, perhaps a new cogen, new technology that's emerging, or we could really rethink our whole energy strategy. And since we were really fortunate to have very visionary leaders, both on our trustees and the president and the provost of the university, as well as Joe Stagner, who is really this is his brainchild. He's the executive director of sustainability and energy management for Stanford. We thought this is an opportunity, and it's an opportunity for us to make a change, to change direction, and to take action. So what you're going to see here is SESI is really about taking action and being visionary, and it's about looking at things better, cheaper, more efficiently, and with flexibility for the future. So that's really the essence of what SESI is about for our group. It's multi-elements that go along with this. There's a central plant, which I think everybody has heard about who's been interested in this project. But that's just one piece of it. That's essentially taking the old cogeneration plant, which burned 100% fossil fuel on campus, generated steam. This is a 120-year-old technology, circulated it through campus very inefficiently. What you might not know is that Stanford heats and cools its buildings simultaneously all year round. So what SESI conceived was that taking this notion of collecting the heat that we're rejecting into the atmosphere. You see the cooling towers, a big pile of steam coming out of the top of the cooling towers. That's all heat that could be recovered and redeployed back to campus to meet our heating demand loads. So we're able to meet 90% of our heating loads by recovering that heat. And that's really what this new central plant does. The central plant is really, look at it as sort of a battery, if you will, a thermal battery. It has 3 huge tanks 2 cold water tanks, chilled water tanks, 1 hot water tank, the red tank there. Let's see if the pointer works on this. I don't know if there's a pointer. Apparently not. Okay, so it basically keeps hot and cold water and then deploys it at different times throughout the campus when it's needed. The heat recovery piece of it is actually one of the major innovations in this project. We have these large heat recovery chillers, which interestingly enough, there are 3 of them in there, and their serial numbers are 1, 2, and 3, because they're brand new pieces of technology that basically takes the hot water, extracts the heat, and redeploys it through campus. As we'll talk about here soon, SunPower is providing a big piece of our renewable energy portfolio. We're going from burning 100% fossil fuels to an all-electric campus. And of that electricity that we're receiving off the grid, 50% of it is coming from SunPower, solar. Thermal system, so we've taken 22 miles of steam pipe and replaced it with hot water pipes. So the steam infrastructure has been removed and replaced with this higher, more efficient hot water system. And then there's a high voltage energy substation, which is going to provide capacity for Stanford for the next 40 years or so. And that's right behind the plant up there. And then finally, the last, one of the most, I think, innovative pieces of this was a piece of software that is developed here at Stanford. It's called, at the time it was called CPOM, which is Central Energy Optimization software. And then now it's EOS, it's Energy Optimization Software, I believe, system. But that's an optimization program. It's taking a bunch of inputs that include energy prices, water, the cost of electricity, and helping determine when to turn on and off equipment so that we can squeeze even more efficiency out of this plant. So there are obviously benefits that come out of energy and water and efficiency. But if you were to ask me, like, why did you do this? You know, what was the compelling argument? I'd give you this slide. So this is that line, that vertical line going up and down there is where we are right now. SESI, the Central Energy Facility, came online April 1st of 2015. And you can see the precipitous decline in our fossil fuel use. If you looked at the top line, this red line at the very top, that would be business as usual before SESI, before we turned that plant on. We're at this point right now. In 2017, when we will have full electrical power supply from our SunPower PPA, we will have 68% reduction in our greenhouse gas. And that's below any of the standards that are out there right now, any of the AB 32, any of the national, international. It actually will allow us today, if we wanted to achieve the 2050 goals. So, and then you can see pretty much the blue and the red lines, they're all fairly minor uses. And when you look at a campus like Stanford, most of it's coming from our Central Energy Facility. You need to have these big, bold moves.
Can you read those to us? We can't see them from here.
Yeah, so the orange is Central Energy Facility. Other university electrical use is blue. Other university natural gas use is red. Campus vehicles are those little lines at the bottom. So from our electricity that we're receiving on campus, like I said, 65% of it is from renewable resources. 50% of it will be from the SunPower agreement. 12% of it is actually the requirement for 33% of California grid electricity to be renewable. So that equates to 12% of our load. And then we are currently deploying an on-campus PV program where there will be about 13 buildings on campus that will be retrofitted with on-site solar as well. So exceeding these targets, this is what I was talking about, that this facility, this SESI program will allow us to meet these targets. We're no longer in the position of trying to figure out how to get to a target. We know that we can get to these targets. It's a matter of really what makes sense. Do we have the flexibility for future emerging technologies to integrate that into this? After I leave here and after Ron leaves here, will the people who inherit this plant have the flexibility to deploy that new technology into the energy supply for campus? What will be the best mix of energy sources for electricity for the campus will be, there will be some capacity to do that as well. And this is sort of the non-energy story, but very important in that as we converted from steam to this hot water, it's a closed loop system. We have saved, on April 1st, the university's water usage dropped 15%. And that's a real key savings here, obviously. A lot of water goes into a steam system. Again, it's a 100-year-old technology, right? It's a legacy system, and the business as usual would be to just keep adding to that system again and again. And a lot of my peers, a lot of my colleagues at other universities, that's what they're with. That's what they deal with: how to do the best next increment. But they still have this huge legacy system, which is super inefficient. So this was not something that we just cooked up and put in front of the leadership, and then they said it sounded like a great idea. We actually looked at 9 options over a period of about 2 years, really. And this was an effort that involved a lot of input from our faculty here on campus. They were tremendous in helping us find the right solution and to consider the right options. But what we call this the bars and bubbles. And the bars and bubbles are, I know you can't read this, so I'll give you just a quick indication. They go from business as usual, which is on the far left. If we had continued to operate the cogeneration plant with the same technology that we currently had and just kept incrementally adding to it, we have an NPV up there of 1.59 billion. And then, so there was another option to say, well, what about a new cogeneration with a new, more efficient cogeneration equipment? And that gets to the second bar, and that's a $1.36 billion NPV. And then you start saying, well, what about looking at converting from steam to hot water? And so that pink bar up the top tells you that these next set of bars are all about hot water. And so you have a new cogen with hot water. You have a gas-powered turbine plus heat recovery. So we're starting to talk about and look at new pieces of equipment like the heat recovery pieces of equipment. You have gas power with internal combustion engines and heat recovery was one we looked at. And then we started to get into, okay, now we're going that's all on-site camp. That would have been replacing our cogeneration facility with an on-site facility. Then we get into this blue box, which is kind of in the center there. There's 2 options. Is going to all electric, pulling from the grid. And you can see we have some benefit there. Obviously, it's a $1.3 billion NPV there on the grid plus heat recovery. And then just all grid pops back up to 1.37. And then we said at the time, remember, this is 4 years ago, a little over 4 years ago that we started thinking about this. This concept was 4 years ago. So I think this came together really fast. But PVs had a whole different feel back then. They weren't life cycling out. It was a demonstration technology, if you were. For us, we were thinking, you would do it to prove that you're being good stewards, but it didn't really make sense when you wanted to look at the fundamentals. And that totally changed. That completely changed. And you can see that the 2 options that we have on the far right are grid plus 20% PV and grid plus 33. And what we went with the one on the far right, and that's where we started in 2011. But even after 2011 started, the solar became so much more compelling. And you can see that box at the top. It shows that our NPV for that option selected, just during the time that we started to develop the SESI program, dropped from 1.267 down to 1.157. So what that equates to is that's a $420 million savings to the university over the life of this project. That's real money. That's I think the guy at the lunchtime seminar from BMW Ventures said, better and cheaper always wins. And I mean, this shows it. But hopefully this shows you that there was a lot of rigor that went into the study of this, and that we're not doing this to demonstrate that we're good green stewards. We're showing you that it actually works. This is new. This is not technology that's yet to be developed. This is stuff that exists today. And we can meet those goals that are out there. This shows that you can do it. And so I think my challenge to my peers at other universities and to other big institutions that have campuses or big projects like this, big infrastructure, why aren't you doing this? This is what you can do this. Given the fact that we were fortunate that we had to make this change because we were at the end of the useful life of our plant, a strategic vision for this, for your energy supply, is really critical, and it pays off. It pays. It's not just about saying that you're green. It actually shows that you can get bottom line savings out of it.
Money's green.
Money's green.
All right, thank you, Jack. I mean, there you go, folks. In 10 minutes, that's the panel in a nutshell. But of course, we have other panelists here. And what I'd like to do is go in order. Ron is the Energy Operations Director, is that right?
Correct.
And I met Ron when I had the opportunity to tour this facility while it was under construction. Ron, this is your chance to go ahead and correct any mistakes your boss made and or add additional information.
Well, great presentation, Jack. I don't know what to add. As Jack pointed out, though, a lot of the comments that I get back from different organizations that have contacted us was this cost prohibitive. And I think as we talk about what we're calling a Stanford solar generating station, added to the cost benefit. We went from originally 300 million, probably an NPV of about 300 million to almost 420 million over the same time period. So very cost effective and environmentally sustainable. That's probably all I'd add. I'm really ready for questions.
That's great, because I got some good tough questions for you later on, Ron.
All right.
How well is this thing working? So, Bill Kelly, please go right ahead. Bill is with SunPower, and as you'll see, they have a significant role in this as well. Very innovative part of the whole SESI project. Let's hear what Bill has to say. I'm sorry.
I have just a few slides to bring up as well.
Take your time, Bill. No problem.
So I wanted to, before I introduce what our role and what SunPower is in the project, I just wanted to kind of comment on maybe what Jack brought up about the project at Stanford. For me, the university is doing something which I see being done at a few other places in the energy industry, and what I consider three attributes is: one is this deep innovation that really a soul searching of what's the best strategy for executing an energy project at a large facility or a large energy use. The three things, I'll point out a few of the things. One, I call clean electrification, that the university recognized the best way to actually power itself and bring energy to the campus is through electricity. Again, given the flexibility to provide it from clean sources ultimately. And how many think of heating with electricity as an inefficient? I mean, if you talk, people when they hear, oh, I'm going to heat with electricity, you're looked at as really a waster of energy. And it's just not true. What's inefficient is, why people think that is the production of electricity is inefficient. And then we're in turn using that in an efficient process from electricity to heating very efficiently. And with heat pumps, you're getting multiples of the input of energy and production of heat. So that's one area that's I see being finally embraced, really converting heating loads, for example, transportation loads to electricity. The other area is this, and you talked about it, Jack, I won't build on that, but basically looking what you're heating and cooling at the same time. It just, I mean, just intuitively, it's like, why are we doing that? But it's not easy to figure out how to change that and what to do with relatively low value heat that's being rejected at the cooling system and recapturing that. So that requires not just, hey, recognition, but how do you really address that? And then finally, Jack brought it up as well, as this energy management systems, like large facilities have those, but basically what we're starting to see is on top of energy management, I'll call it the energy and economic engines, that looking at the, the platform of your usage and the cost of energy, how do you actually optimize that to deliver savings for that? And so, and I think there was a speaker at a panel earlier today, Enernoc has got a business model kind of around this, is that there's really kind of an emerging, not technology, but software to really help large customers optimize both usage and cost of energy. Then it's hard to build. It's a heavy lift. I called it here, miles of pipes, and from the engineering work up front, the real detailed engineering work that's done, the building of the system, and then the commissioning of the system, getting it to work. And then finally, and this is really, I learned this was underway at Stanford at the ribbon cutting, is John Hennessy spoke at that. It's like he knows the project, right? And I was wondering how is Joe Stagner and Jack, how are you guys pulling this project off? And you realize that it's executive leadership. When the executives take on the project and sponsor the project, it changes quickly and things start happening. And so what I think is pretty inspirational that's going on in energy is that executives at companies and within the government are basically saying sustainability is important. We want to start sponsoring bold initiatives, and I think this is a real example of that. So from that, SESI, or the Stanford Energy Systems Innovation, was kind of born and built, right? You guys have got a lot to be proud of. I'm a Stanford grad. I personally feel really proud of the work that Stanford's doing. There's a lot to be proud of at being a Stanford alumni, but this is really probably the biggest thing I think that Stanford's done to really take leadership. 68% reduction. I mean, that chart is like, welcome to 2050, right? We're here. We're really doing some big things. I also wanted to acknowledge, this is, SunPower's role was basically providing a big chunk of the clean energy that's coming into the campus. I'll introduce myself. My name is Bill Kelly. I work at SunPower. I've been at SunPower for 12 years. SunPower's technology was actually born at the university in the mid-80s. And so the cell and panels that we manufacture, the technology was invented here at Stanford. And we're known for the highest efficiency panel, but also the cells and panels last for a long time. The persistent performance, they're really durable. And they should last beyond 40 years, the systems that we're installing. So I think your window of evaluation in the MPB was probably 30 years? 35 years. So SunPower is delivering 73 megawatts of capacity, around over 150 million kilowatt hours per year of energy. It's coming from what will be called the Stanford Solar Generation Station. This is located in California, but not on the campus. It's called an additional capacity. So Stanford owns the energy that's coming from this plant. This is Stanford's plant. And it would not have been built if Stanford didn't. It's not as if it's a repurposed plant. It's really an additional capacity that's brought onto California's grid to support this project. So that's a big component of it. And then we're providing distributed generation on, I think it's 13 buildings or parking structures, not parking lots, parking structures on the campus. So installing PV on 13 sites. I wanted to, as a footnote, this is, again, I think I call clean electrification. Actually, the term I like for it is getting off the pipe. I did this for my home, for example. I had converted all my heating and hot water loads from gas to electric. I've got an electric car. It's kind of increasing your dependence on electricity, but cutting the use of natural gas. But the Exploratorium, how many here have been to the new Exploratorium? Oh, that's great. So they have similarly completely going with an electric heating and cooling system, and they're providing about 100% of their energy from photovoltaics on the roof of the Exploratorium. And they have kind of a nice display of this, actually, that you can see the heat pump systems that are in place if you guys get a chance to visit the facility. So with that, I just wanted to just point at Gil. I wanted to, every time I think of the work that I do, I took classes from Gil here at Stanford. CE 176, was that the course? Small scale energy systems, really inspirational. It's like I didn't study in civil engineering and mechanical engineering, but that changed my course and really getting into energy. And I believe there are thousands of students that you've influenced similarly in clean tech. So thank you. Thank you. Yeah, that was it.
Great. Yeah, we can all give a little bit of thanks to Gil Masters. I took Better Homes and Garbage the first year he provided the class. There he is. And Jim Sweeney's up here too. These are gentlemen. Any other faculty here from Stanford? There's a gentleman back there. How many students are here? Good. I want to make sure some students ask some questions of this. So if I may, I'll stand over here a little bit out of the way. I think the presentations that you got really give you a sense of this project. And without a doubt, it's really extraordinary. Having been a former energy commissioner and the policies that we try and put in place in this state, you've far exceeded what we're trying to accomplish. And you've set a new standard and a new goal for others. It really is an extraordinary concept. They had student participation, I know, early on in all of this, and the sales job that you did internally in the university and with the board of directors. I think you had a little help in that Mr. Hennessy is an engineer, and that might have helped a tad as well. How many engineers in the audience? Okay, well, you know this stuff better than I do. I don't want to let these guys off the hook easily. I know a little bit about thermodynamics, having been an engineer myself. I've read everything about the project. From its inception, I read the independent consultant's analysis. I'm a little skeptical. I don't think it's going to work. So I'm going to direct this one to you, Ron. There'll be some softballs later on, but let's start out here with the big question. This is pretty new and innovative, and with new comes uncertain. I've asked Ron before, how's it working? When are you going to get the results? And I don't know if it's for job security or what, but he says, oh, in about a year. Ron, do you believe this is going to work, and why?
Okay. Well, not only do I believe it's working, or that it will work, it is working. As a matter of fact, we brought the plant online March 24th in the middle of the night, just so that we could preclude any anxiety.
Without telling anybody, you brought it online.
Essentially, yes. I think we told Jack the next day. So it's actually running quite well. As with any new facility, there's some commissioning things we're working through. You can't put 5,000 instruments together and not have some things to work out. So it might be, like I said, a year before I have really good data. I need to go through a peak season of summer and a peak season of winter. But I can tell you right now, we're already meeting our design goals. The other day, looking at data, we're getting a coefficient of performance on our heat recovery chillers. It's just around 7, which is phenomenal.
There was some purposeful built equipment for this that was
absolutely unique. So our heat recovery chillers were designed literally for this project. So some data if you're interested. By the way, I want to say that we have a website, sesi.stanford.edu, that all of this information, the presentation, and a plethora of information is there. All the why we did what we did, and really a lot of data about what we're doing is on that website. So I encourage you to go there. The heat recovery chillers, they're 2,500 ton chilling capacity simultaneous with 40 million BTUs of heating capacity. To have that type of device hasn't been done on that scale. And, you know, as Jack said earlier, all that waste heat just going out into the environment through a cooling tower, that's normally how, if you saw the old cogen run, we had a 5,000-foot high steam plume coming out of it. Well, now we're capturing that heat at the same time as we're meeting the cooling needs for the campus. So very innovative in that idea. The other thing I want to point out that I don't know was brought out is in the transition from steam to hot water, we went from about a 15 to 16% loss rate to less than 4%. The numbers I looked at the other day were at about 3.68% loss rate. That's a full loop cycle loss rate. That's phenomenal. You're not going to get that with steam. I've talked to my colleagues at the city of San Francisco, and they're running almost 30%. So if you see the steam plumes in the city of San Francisco, that's where that energy is going. So from a loss rate, you know, you could talk about water, safety, but just pure energy efficient was a huge improvement.
So Ron is you know, I couldn't believe it. While this thing was finishing up construction, just before commissioning, he's always so calm. And I know this isn't the first rodeo for you. You've built a number of things like this, but this one's kind of unique.
It is.
And you know, I can't believe the GHG reduction numbers, Jack. They're just extraordinary. Would you say 68% are projected, and 15% savings on water. Do you think this is a model for other campuses, be they university and business? And I think we know the answer is probably yes, but are they stepping forward yet or not?
Well, yeah, the short answer is yes, absolutely. Other universities and campuses can deploy this. I mean, I think there's, Joe was telling me that, you know, 30 to 80%, you know, depending on where they are in the climate, they can recover between 30 and 80% of their heat and redeploy it. So it is very feasible for other campuses. I think, I have to say, being involved in the sort of the operations of a campus now for at least, you know, 7 years here as the head of operations, that there was a lot of emphasis on making these big goals back in 2007 and 8. And you know, our leadership resisted it, and they said, you know, that these are kind of false goals. You've really got to, how are you going to get there? And one of the things that we did, I think, that was really critically different than our other peer institutions was we took this notion of what is sustainability, you know, the office of sustainability, if you will, and made it part of operations. So our sustainability folks are operational folks, and they know what it means to try to implement something. So rather than just making these policies of saying we're going to be so many % better by 2020 or 2050 or whatever, you know, we had people who actually knew how you could do it, and I think that made a big difference. I think that's kind of what set us apart, frankly. That's not to say that we don't have that aspect of sustainability here. It's really sort of on the demand side. You know, how do you improve behavior and make people more aware, and that's really important, and we'll always be doing that. But that's not going to get you that big drop, and that big drop's only going to come from big moves. And we were just really fortunate that we, you know, had leadership that had a vision at the time that supported it.
So I'm just taking it off. I'm taking it off of the Exploratorium and putting it back on Stanford. Here's what I'm going to do. I'm going to ask one more question to Mr. Kelly. I'd like to open it up to the audience for questions because got a lot of students in here. I'd really like to give some preference to students if you've got some questions. Anything's open here. Engineering questions, policy questions, even how they sold the university on this idea. That's part of what makes this extraordinary. And of course, questions of Mr. Kelly. So Bill, the question I got for you is, what can you tell us about the agreement that you struck with Stanford? This is a big project, 73 megawatts. I mean, if this was a thermal project, you'd have to go through the Energy Commission to get this permitted. This is big. Where's it being built? How much money is it going to cost? Or what's the PPA amount for? How long until it's online? And how are you going to get the power in here? I mean, that's a complicated process, and I think everybody would benefit from understanding a little bit more how you circumvent the laws. That's not there. Navigate. Navigate. That really was a mistake.
How do I circumvent the laws?
No, of course not.
Is that a commissioner
So,
question?
Bill, I'd like you to answer any and all of those.
Any of all those. There are some tough questions, actually. Some of which I think I'm going to avert answering. One
Sure.
of which we've been asked a lot. Where is the plant? And we're saying it's in California. And the reason we're not disclosing the location is that it's permitting interconnection processes that you end up a lot of that is better done basically through the regulatory bodies, the counties, and the ISO for interconnection process. So
And quietly.
And quietly, yeah, because we've got a really ambitious plan to get that online by the end of 2016. So it will definitely be online by 2016. Actually, we believe we're going to start producing.
That's extraordinary.
By the end of this year, we're expecting.
Okay, so I understand that. I understand why you need to keep quiet on that at this point. But what else can you tell us about the agreement?
So it's a 25-year agreement, and I'll also mention that the energy price is flat, so that there's no escalation in the rate. And the rate, I'll leave it to Stanford's discretion as to disclose that. I'm sure you will. But basically, it's competitive today with current rates and doesn't escalate. So in my view, what's really impressive is that you're paying the savings will just build over time. You really are managing the risk with energy price inflation. The other thing is that Stanford is not averting the laws. They're fortunate, and unfortunately not all of California has this option, but they're a direct access customer. So in other words, they get the choice, or Stanford gets the choice in where to get its energy from. And so that we can produce energy actually any place in California, feed it into the California grid. It's regulated by the ISO, and Stanford can own that power and purchase the power from us.
Right. So essentially, you had to have that direct access ability. You can't go back and get that unless legislation were to open up to change that. So I'm going to turn it back to the panel to see if Jack would like to add anything else. Please, let's have a few folks line up for questions. I'll come with you, Jim, first, okay, on the question. Let me let Jack see if he wants to add anything to that.
I don't have much to add about the specifics of the actual agreement, but to let you know why, how much electricity we were thinking about committing to at this point was a lot. We had a lot of discussion about that, and our leadership had some varying opinions about it, frankly. And it came out that it was really important that we had optionality and flexibility going forward. That we weren't today locking ourselves into the technology that we know today's technology 25 years from now. Because if you look back on what that was, we would have taken a totally different route 25 years ago if we knew that, right? So, so I thought that was really. I think that says a lot about the stewardship of the university by the president, who's going to be turning over the reins. He's left. There is some flexibility in how we do this in the future. So, I think that says a lot about the leadership.
Okay, so is SunPower paying you money in order to be on to have Stanford as their customer? I'm just kidding, of course. It's a pretty prestigious opportunity.
I will mention I was part of the team that proposed to Stanford, and we brought the founder of SunPower to the interview, who came from Stanford, So we did try some pretty cheesy sales.
I'm sure it was a very competitive arrangement.
I'll admit.
So I asked. Thank you for standing for questions. I'm going to go to you, but first I'm going to go to our conference organizer and another professor at Stanford who's influenced a lot of students over the years, Jim Sweeney.
This may have a question mark at the end, but it may not. It's just a comment to everybody about an element of the process that wasn't described. Often when you have universities, you have somebody doing sustainability. There's operations, and you don't get tied into the faculty. This group had to go through a gauntlet of faculty members who were we had a task force of Lynn Orr, who's now the Deputy Secretary of Energy, Chris Edwards, who is a world expert in thermodynamics, John Wine, who's headed the energy modeling forum and looking at the economics and forecasts, Larry Golder, who has been chairman of the economics department, and myself, all looking at, and they had to be ripped apart all the way. And so at the end, I have to believe that this helped market it to the university because they went through the gauntlet and they willingly put themselves through the gauntlet. So I thought this was one very exceptional element of it. The other thing that didn't quite, maybe I missed it at the end, that when we think about the duck curve in California, the solar coming in, creating problems, notice how these fit together. We have the solar that's heating the water in those massive tanks, so you can heat the water at the times where you have the electricity, and you can leave it all the time, and so we can have the district heating and cooling system that can be fully matched to the availability of the electricity. So a system like this actually helps with the duck curve rather than makes it worse. So for me as a faculty member looking at it, I said, got to be pretty proud because it's environmentally and economically way of implementing energy efficiency and integrating renewables in the system in a way that really works, that didn't at the end of the time create a conflict between those. So I guess I said I need to have a question. What's the serial number of those chillers that are those great big green ones in there? Could you...
the green ones or the orange ones?
Well, maybe the ones that have the low serial number.
I
Could
hope
you
you
tell us?
mean the orange ones.
1, 2, and 3.
Serial numbers 1, 2, and 3 to suggest what they mean by innovation in the equipment. Thank you for that.
2013. 201.
Okay, so we have plenty of time for questions, and please identify yourself and go right ahead.
Hi, my name is Ed Carley. I am a recent graduate of American University's Kogod School of Business Master of Sustainability Management. American University recently purchased 50% of their power from solar as well. So I had some questions, just very familiar with AU's process, and I'm curious, how was the deal brokered between Stanford and SunPower? Were there a number of other competitors who came in? Did you make any agreements to ensure that the power was delivered from the yet undisclosed location to Palo Alto here? And I'm just kind of curious about the nitty-gritty of the deal. Thank you.
There were, I believe, 4. Well, first of all, we had a consulting firm called Energy Edge, who really turned out to be terrific help to us in sort of negotiating really unknown territory for us, and I think for a lot of people in the industry, frankly. And we had a list of 4. I think we shortlisted it down to the 2. It was a very competitive situation between SunPower and one of their competitors, and they came in with the better deal. And you know, as for the you know how we came to the terms, it was just as hard as any other construction contract we do. There's a lot of negotiation, a lot of you know, faith in the other side that you're going to deliver what you deliver. I can't really speak to whether or not that electron is going to go from the Central Valley to here and be accounted for.
Yeah.
No.
Yeah, so our number one, contractually, I think we're obligated to deliver the energy that is under contract, but the energy is delivered to the bus bar in California. And the way I look at it is that energy is being produced by Stanford, and they're getting some economic cost associated with bringing that onto the grid. And there's a separate, they're consuming energy and paying for that. So that it's not the same electrons. I don't consider them the same electrons. And I think Mr. Sweeney had mentioned is that you've got to be concerned if you're producing a lot of electricity during the day and the price fluctuates. Right now, that's a benefit, but over time, as more and more renewables and solar in particular come onto the grid, what's the cost of buying it? Does it match the price you're paying it? And so Stanford's got this great flexibility in SESI to actually match the load profile with the economic forecast, so that they can consume actually more during the day if that's the best proposition. So we're committed to delivering out a bus bar into California, and then Stanford's basically responsible for buying that power at the agreed upon rate. It's pretty simple in one regard.
Please identify yourself. Well, thank you. And I'd like to add one thing. You know, it's not like Stanford, this is their first construction project. Anybody on this campus knows there's like a dozen cranes here at any one time. And of course, I think in Ron, they've hired one of the best, but it's extraordinary. And I'm sure they negotiated a very tough contract with SunPower. Yeah. Please identify yourself.
Yes, my name is Bruce Carney. I'm with Carbon Free Mountain View. I'm also a Stanford alum. And I agree with Bill that this gives all Stanford alumni something to be very proud of. One thing I've never quite understood is how much of your electricity you got from Cardinal Cogen before. So can you explain how much of Stanford's energy came from PG&E pre-project and now post-implementation, particularly when all the solar is online?
Good question.
Well, I might get into trouble here. I'm an architect by training, so when I start talking about engineering things, I can get lost. But Cardinal Cogen supplied all of our electricity except for some de minimis amounts we got from PG&E, some various accounts. There are probably, I don't know, there are probably a couple dozen PG&E accounts that, for various reasons, you know, they're not tied to our system. So, I mean, that's the reason you see that such a precipitous drop in that in the GHG is because it was 100% of our fossil fuels were being burned on campus and supplying most of our electricity, and our thermal services. So it's a significant amount. I have to say it's in the 90%.
Over 97%.
97%.
And post-project?
He's doing great.
It's 100% from the grid.
It's 100% from the grid. However, you said post-solar, right?
Right.
Once the generating station is online, 50% of our power will come from that solar generating station.
Okay. Well, but 65% of it will be solar because we'll get, the grid has 33% from renewable sources anyway.
Perfect, thank you.
And then we'll have some 3% on campus.
That's right. When you were doing the Cardinal Cogen, you weren't getting the benefit of the policies we've implemented to count that 33%.
So if you didn't do the math, that's about 65 to 68% will be renewable.
Please.
So I'm John Massey, TechVisor Consulting. So given the things you got up on the screen, can you say some more about the interactions with the executive leadership? Right? What sorts of questions did they ask? Did you change their minds on things? Did they change your minds? I should explain, I've known John for 30 years and worked with him at MIPS, so I kind of know how he works. So I'm just curious how these interactions worked.
Well, they were critical. As Jim said, the leadership, particularly the president, was key in setting up a sort of a governance structure, and they were key in getting the faculty involved and helped us identify the right faculty to look at the system. He set up an ad hoc committee of the trustees, so there were a group of maybe 5 or 6 trustees that focused specifically on this system. And it went through its normal Board of Trustee approvals. They were critical. They made the project much better. They made it a much better system. The faculty involvement made it a much better program.
Please.
Hi, I'm Lena Perkins. I just finished my PhD in mechanical engineering, and
congratulations.
I helped catalyze Chris Edwards' involvement, which was a little bit tumultuous at the time, and I'm really glad that everyone was able to come to such a win-win solution in terms of energy rational and the university being protected financially with the power purchase agreement. I have 2 questions. They're both somewhat technical. So these heat pumps.
Good.
Yeah. So these heat pumps that you have, what is the fluid that's being used? And did people look into the global warming potential of that cycling fluid? Because I worked on an organic Rankine cycle device, and that, you know, there's varying options. And then my second question is, with I mean, we don't think about it as much now post-Enron, but like, you know, with the rolling brownouts and sort of the focus on energy security, when you have a linear accelerator in a hospital on the campus, you know, how much, you know, those aren't the same electrons, you know, that are coming across, and how much did that factor into it, and how, I mean, you can provide some buffering and storage thermally with this, but how much anxiety did that cause?
Me tag in?
Yes.
All right.
Yes, please.
So to begin with, we like to call it a heat recovery chiller, because it's more than just a heat. It is transferring heat, but it's creating chilled water and hot water at the same time. So heat recovery chiller. It does use a refrigeration cycle. It uses R134A. So that's a refrigerant, which is compliant with the fluorocarbon rules.
So not great, but
not great. It's you know, there's a huge trade-off on all the different refrigerants you could use, and that's the most efficient for our process that is environmentally compliant. Then I have a short memory. I'm sorry. What was your second question?
Reliability.
Oh, brownouts, reliability. So, you know, one of the big innovations we did here, you know, the question, and this is a great question, I get this a lot, is, you know, hey, we used to have our own power plant and we were reliable with that. Now we're trusting on direct access on the grid, and what's that going to do for reliability? I have to tell you, our old plant used to trip about 7 to 9 times a year. So the reality, the grid reliability is in the 3rd decimal of nines. Very reliable. We have our new substation has 2 feeds. So I don't know if I want to get into a lot of detail.
No, go ahead. That's all right. Go ahead.
We have the Cooley Landing feed, which comes across the bay. Then that provides us tie-in to the south. And then we have the Jefferson Ridge tie-in that comes from the north. So we have a very reliable feed of power, and we're able to switch that within 3 to 5 cycles. So it's actually pretty quick. Reliability of the campus from a energy delivery is much higher. And then, of course, you asked a question about providing for the hospitals. Well, we still do have on-campus emergency power. I have that at the facility as well, if need be. And just to clean up one question you said about SLAC. SLAC actually gets its power through a DOE contract, and I don't actually provide that. Although we're working on a deal that we may announce later on. So.
And the hospital gets it from Palo Alto.
Exactly.
I mean, this is extraordinary. So you have a static transfer switch. At what voltage and how many megawatts?
Our substation runs at 60,000 volts. We get it from 230,000 out on the grid. Our substation goes from 60,000 down to 12,000. So I have 5 transformers with switches.
How many megawatts can you switch? Because that's three milliseconds, I think you said, or 3 cycles, is quick enough that you're not going to lose stuff on campus. So
we hope not.
So how many megawatts? How many megawatts are you switching?
We bring in about a peak load of about 45 to 50 megawatts. Our substation is designed to handle up to 100 megawatts, which was a huge improvement over our old substation, which was capacity capped out at about 60. So our normal load on campus is about 30 to 35 megawatts.
Wonderful.
Yeah, if I could, a couple questions came up before about the deal between SunPower and Stanford. I wanted to mention, people may not be aware of this, but this is actually pretty new within the solar industry, that commercial customers are buying power remotely. American University is actually one of the very first back east under the PGM circuit. So I think that is really notable, that large end customers, almost all the renewables at utility scale were being bought by utilities. And so I'll mention, and I don't think they mind, Apple Computers is one of the companies that really stepped out and said, hey, we want to get more renewables, so that they felt like Stanford, one approach was to actually acquire the renewables themselves rather than relying on the utilities service to provide that. So that is actually a big movement right now within the renewable industry, that we're able to actually access customers that have big renewables appetite directly. You need an unregulated market, either be direct access in California, PJM and Texas are largely fully deregulated, those markets, so those customers in those areas can go directly to companies like ours.
So our high-tech companies are also innovative. In fact, I noted this morning, Google just built their 14th data center in an old coal plant. So there's another use for old coal plants. So Don, come on forward. This is Don Bray, joint venture Silicon Valley. And Don, before you ask your question, students ask the best questions. Any students here that have questions, please go right ahead. Don. No, Don, you're first. You're Don. Don, you're first.
I'll just sit down. Continuing in the speeds and feeds vein that we're currently on, I think you mentioned the campus is about a 30 megawatt load,
roughly 30 to 35 generally,
and
actually peak of 42.
Yeah, how much of that is electricity used for heating and cooling versus all other uses?
That's a great question. So, you know, at your home, this is my sales pitch, by the way. So at your home, about 50% of your home energy is for HVAC, heating, ventilation, and cooling. Our facility, the central energy facility itself, uses about 1/3, about 34% of the campus energy, which is the direct answer to your question. But if you think about it in terms of heating and cooling, normally being about 50%, we have about a 16% efficiency by doing it the Walmart way in volume with very efficient heat recovery chillers.
And then kind of building on that, and then I'll sit down and let students ask questions. How many hours worth of storage do you have in hot water and chilled water, and what type of day represents the biggest challenge? And maybe you haven't gotten there yet because it hasn't been online that long, but does a particularly hot day or a particularly cold day mess with, or you know, most challenging system?
Great multi-part question. See if I can remember them all. So to begin, I'll do it backwards. So a design day is what we base our capacity on, and a lot of it is based on OSHPD rules, which is the California Office of State Higher Health. I almost said pricing and delays. Health and Planning and Development. Oh my God! Hope that's not being recorded. In any event, they're based on a lot of rules because we supply all of the thermal, not all of it, but most of the energy for the hospitals and research park. So we have a hot water tank that is about 2.34 million gallons, the largest one that I know of in North America, believe it or not. And it is designed to handle the load for the campus for up to 24 hours. It contains 600 MMBTUs of thermal energy. The chilled water is 90,000 tons of cooling, and that's based on the same ability. It's actually 72 hours of supplying the loads for OSHPD loads. That gets kind of, you asked a technical question, there's the technical answer.
So 3 days of ability to back up the requirement.
The critical loads. What it will do, though, is it'll meet the entire campus demand during an entire day. So, you know, you don't use all of your heat in the morning and the evening. It's through an entire day with a peak, you know, 3 to 4 in the afternoon. We can actually meet, a matter of fact, right now, I have no equipment other than pumps running at the plant, and the campus is being cooled. We're being cooled right now off of thermal storage. Does that answer your question?
Yeah, very good.
Okay.
Please identify yourself.
Hi, my name is Brian. I'm a current public policy master's student, also a former alumnus of Guild Masters' class too. And so my question, I was wondering if you guys could go back to the idea of scalability for other campuses as well. I think I would be interested in knowing some of the challenges other places might face. So one off the top of my head is that Stanford has a lot of land available here for something like a solar facility, and maybe you go down to, I don't know, USC pops in my head immediately, where it's kind of like right in the middle of the city. How do you put something like that on different college campuses?
Well, so our solar, so the solar's not on campus, right? So and believe it or not, we have 8,180 acres here, but a lot of it's very constrained. And so, you know, one of the reasons that we've looked at this sort of institutional scale solar or larger scale solar. But other universities, you know, we're really fortunate in our climate here, and so, you know, that has a lot to do with I think, the really aggressive goals. And if you're going back east, it's a lot more difficult for them to kind of reach maybe these stretch goals. You know, there are places like Ball State and Auburn and others that have back east that have done heat recovery and have done this district heating. It's a great success. And so I think, you know, it's just really hard to make a big change, and it takes a lot of capital. I mean, we invested a lot, $485 million in SESI, in order to gain these long-term savings over time. And many, as you know, many state institutions, particularly the universities, can't make that kind of investment. So we're very fortunate that we had people who, you know, were willing to make that investment in the future and could do it. And I know a lot of my colleagues are really struggling with it.
Thank you.
So in the interest of time, I believe we're just about perfectly on time. I'd like to ask each of you if you would just take a minute or so, any concluding remarks, things that we didn't get to, corrections that you'd like to make, whatever. Let's go back down the line. And Bill, if you'd go first, I'd appreciate it.
Yeah, I think maybe I'll conclude with, people are asking who else can do this, and I'll take a little bit of exception, Jack, to your comments. I feel like it is true Stanford has got a capital access that's unique. I mean, the credit rating is phenomenal, right? You guys can do a lot. But I think that the technology really works. I mean, you're demonstrating that it's got economic performance, and capital can be brought in from investors to invest in projects like that. So I would say, not challenging you, but I really feel like there's other large universities, large campus type companies that really can do something very similar. And I would, though, agree in mild climates, you know, the heat recovery and the use of heat pumps is really a unique, you know, opportunity. I would say that there's so many campuses, just universities, that installed cogen in the 80s. You know, if we just basically, if they replicated what was done, those that are in the proper climates, they could make a big impact. But I guess, and then finally, just I'm really glad that companies and large leaders like Stanford that are jumping into buying renewables directly. It's really helping our industry.
Just very quickly, you know, we talk a lot about putting this type of change. It's multiple innovations, which is, I'm glad we used it as a plural, but it's not just universities. The city of Copenhagen in Denmark, St. Paul, Minnesota, a municipality district, they are adopting this. Obviously, it's at a different scale, but they're working towards redoing their entire heating system from steam to hot water. Heat recovery is possible even in Minnesota. It's one of the coldest states in the union. And they have, I believe, a 33 or 34% overlap. So it is possible. You just need to take the time to look at it. I encourage you to do that. There is value there. And lastly, just a plug for our website. A lot of the data that we have is on there, sesi.stanford.edu.
Jack, your final remarks.
Just finally, you know, I think we've been really fortunate to have a utilities group, for lack of a better term, that's visionary. And, you know, not just trying to keep up with demand, but thinking about what's best for the university in the long term. So that's been, I think, really key to sort of directing the ship through all of the scrutiny that went into it. And it's also a huge team. I mean, we had partners along the way with the city of Palo Alto, with the siting, with the county of Santa Clara, again, our faculty, our project management group who delivered this project in 4 years from concept until we turned it on. It was 4 years, 22 miles of pipe, 160 buildings converted, you know, that plant out there with all that technology. It just, you know, it was the right people at the right time with the right leadership.
So I applaud you all. Before we do, however, I'd like to remind everyone it's break time following this, and we're going to pick right up on time at 3:50 for the keynote back in the main room. But before you leave, gentlemen, congratulations. I'd like to thank you all very much.